Thank you. Hello, my name is Jaeseok from South Korea. Today, I'd like to talk about wealth distribution in agent network, talent, and network structure matter. Let me begin with two popular principles of economy. Malthus pointed out the exponential growth of the population, and Pareto discovered that 80% of land in Italy was owned by only 20% of the population. This is now known as Pareto rule or power distribution. The interesting fact is that wealth satisfies both two principles. To describe individuals' capital, we mainly focus on this stochastic differential equation. This equation consists of three major factors: talent, luck, and social interaction. Here we denote model parameters. C is capital and T is talent. T is time. Alpha is a percentage drift, increasing function of T. So it makes the more talent gives the more capital. And beta is the percentage volatility as a function of T, determines the fluctuation scales. W is the Wiener process that makes random fluctuations in capital, so it corresponds to luck effect. The last two terms correspond to capital transfer through exchanges between agents. The first term is export of I to J, and second term is import of I from J. We introduce interaction coupling constant Jij as pooling and sharing interaction. In this scenario, each agent gives capital as JDT over JDTC over K to all other neighbors. When agent I and J have same capital, I receive more capital from J. So we refer to this property as high degree advantage. Sorry. Yes. Our model addresses interactions between heterogeneous agents. So it is generalized version of the TVL model and BM model. So before moving on to TLS model, we must take a look at TVL model to know the origin of alpha and beta. This is a microscopic representation of the TVL model. In this model, all agents start with same capital, C0. For a luck event with probability A, the agent takes a random number from a uniform distribution between 0 and 1. If this number is smaller than agent talent T, the capital multiplied by R. It implies that the more talented agent catches the more opportunities for additional capital. For an unlucky event with probability B, the agent capital just divided by R. And the talent distribution follows the normal distribution. If you let L as the number of capital gains minus losses, the TVL motion can be considered as a heterogeneous random walk in the L space. When an agent moves forward with probability GPGDI and moves backward with probability B. Therefore, we can derive a continuous equation for L as shown at the top. Since PGT is increasing function of T, the higher talent gives the more drift to positive direction of L. Also, it can be rewritten as a geometric Brownian motion for C at the bottom. Let me share some interesting point of the TVL model. After 80 times steps over, we can get capital histogram on the right. Our interest is whether a large amount of capital actually comes from high talent. So the answer is no. The left panel shows the relationship between capital and talent. The most successful agent's talent is 0.61, and which is almost same as the average talent of 0.6. The right panel shows the relationship between capital and luck. The log-scaled capital is proportional to the number of lucky events. The interesting point is that in the TVL model, an individual's success is dominated by the luck. It can be understood from the equation of the TVL model. For the given parameter set, beta is much larger than alpha. So individual success is dominated by log for short-term regime, and also inequality is originated from large fluctuation. Since the TVL model is non-interactive models now we introduce simple mean-field interaction. In this case, agents with more capital than the average will lose the capital, whereas those with less capital will gain additional capital. After a long time, the normalized capital distribution converges to equilibrium. At that time, the distribution has the Fowler tail with the exponent gamma is equal to 2 plus 2j over beta square minus delta. Here, for various j, we can get the following distributions. As you can see, large j and small beta reduce the capital variances. Therefore, 2j over beta square is the key control parameter for stationary distribution. However, gamma can also depend on talent distribution, but it is complicated. This is summary of simple wealth dynamics models, and here are some remarks. The TVL model exhibits non-exponential growth, and whereas the mean-field TLS model exhibit exponential growth, and moreover, the geometric Brownian motion and TVL model have same gamma. But the mean-field BM model and TLS model do not share the same gamma. This is a recap of the TLS model, and there is unique consideration for general network case. Since the talent distribution follows the normal distribution, there are many cases that allocating talent samples to nodes. Indeed, capital dynamics is influenced by talent allocations. So we now focus on the talent allocation issue as talent configuration effect, simply TC effect. As illustrated in two network pictures, where nodal colors correspond to nodal talents, and we quantify talent configuration properties as two measures. The first is talent adsorptivity, simply TA, and the second is talent degree correlation, simply TD. TA indicates how much similar talents are connected in network, and TD indicates how much larger talent tend to have a larger degree. We use these three economic indices to estimate the TC effect. Growth rate shows how many times system has grown, and Gini coefficient shows the relative inequality of system, and meritocratic fairness, simply AT correlation, shows the correlation between talent and capital level. I'm sorry. Here are results at the same time for Parabashi-Albert network and Watts-Strogatz network, where the same mean degree as 2. Here are some remarks. First, almost all indices have positive correlations with both TA and TD. Second, the realization error only varies with TD in the BA network. This error bar is realization error. Last, anti-meritocratic society is impossible when TD is equal to 0, because LT correlations are positive for all TA. Below are more detailed interpretation. So first, there is trade of relation between growth and equality because growth rate and Gini coefficient increase together, like this. So over TA and TD. Second, high TD in the BA network leads to the entire system depending on the performances of few key agents. So this hub plays few key agent behavior. This figure shows simultaneous TC effect for BA and WSN network. X and Y axis show TA and TD respectively, and the colored region are expected value of the indices. In this figure, we can see that which one is dominant for indices. For example, growth rate in BA network, contour lines lies horizontally. So BA network is sensitive to TD. In contrast, the Gini coefficient in WS network, contour lines lies vertically. So in that case, TA is dominant. Here is the summary. We introduced the TLS model and investigated the role of talent configuration properties on capital dynamics. The first result is that growth rate and Gini coefficient and meritocratic fairness are positively correlated with TA and TD. It shows that socio-economic homophily makes a social dilemma between growth and inequality. And the economic growth strongly depends on performances of hubs. The second result is that capital dynamics on scale-free network is more sensitive to TD, and lattice-like network is more sensitive to TA. I'd like to show a couple of ongoing research briefly. Even though TA is defined as Pearson correlation coefficient, it doesn't mean that -1 and 1 are minimum and maximum values for general network case. However, for one-dimensional periodic lattice case, TA value can reach -1 and 1. Therefore, these are good examples to check extreme TA effect. This figure shows long-term LT correlation evolutions. Maximum and minimum TA are represented as red color and blue color. For most cases, LT correlation grows slower than TVL model. This dotted line is TVL model. So, however, if TA is 1, LT correlation grows much faster than TVL model. This result implies that if talented agents help each other, it promotes the meritocratic society. One more interesting thing is critical behavior of LT correlation. Final LT correlation discontinuously increases at TA is equal to 0. Next, let me consider condensation transition. These figures show initial capital distribution on the lattice space. Node color represent talent and node size represent normalized capital. Here are some animations for each condition. Yeah. This figure shows capital distributions after a long time. When TA is equal to 0, capital clusters are randomly distributed. And its size variance is very small. Also, even lower talented agents, such like blue dots, can hold a large amount of capital. However, when TA is equal to 1, capital clusters are concentrated at center. Its size variance is very large. Also, lower talented agents cannot hold large amount of capital. This phenomena is deeply related to the wealth condensation. As shown in the left panel, the Pareto distribution have a critical point of gamma as 2. Therefore, the gamma is a key indicator of Wells condensation for Paulo-Tailed distribution. Centered figure shows double logarithmic growth for stationary distribution. For each case, gamma is larger and smaller than 2. Therefore, transition from non-condensation state to condensation state is possible as TA increases. You can access our preprint through this QR code, and thank you so much.